Hi everyone. My name is Qinyu Zhang, and I'm with Northwest University in Shenzhen, China. Today I'll be presenting our paper, Walking in the Wild, Safe and Natural Redirected Walking in Open Physical Spaces. This is joint work with Xinda, Guoqiang Yang, Yunchen Li, and Guohua from Northwest University, and Jian and Lili Wang from Beihang University. Classic redirect walking is usually built for a bounded lab setting. The layout is known, obstacles are mostly static, and safe paths can be planned in advance. But real deployments, like location-based VR venues, are open, shared, and dynamic. People move, obstacles move, and you often don't have a reliable wall or boundary map to plan against. So our goal is twofold. First, preserve natural guidance so users can keep walking the way they intend, and second, ensure real-time collision safety without depending on a fixed boundary model. We capture this challenge by formalizing it as a new task. We call this OPS-RDW, short for Open Physical Spaces Redirected Walking. At each time, t, the user is in state, xt, the environment evolves over time as, et, and the user has an intention, captured by the desired virtual motion, u sub t. Our system outputs a safe physical motion, ut, which generates a physical path, pt. While enforcing a key safety requirement, the user must stay at least a minimum distance away from every obstacle. The objective is straightforward: follow the user's intended motion as closely as possible, while remaining safe. In other words, we minimize so, where do existing approaches fall short? Geometric methods like S2C and S2O assume static, fully known environments. Perception-driven methods can be calibration-heavy and don't always cope well with rapidly changing context. Learning and multi-user methods often depend on prior models or degrade in dynamic public spaces. The gap we target is a learning-free, model-light approach that enforces real-time safety constraints in open tracked spaces. That leads to our method, DyCoRe. DyCoRe takes the user intention and the live environment, then runs a closed-loop pipeline. 1. Build dynamic safety constraints using dynamic control barrier functions. 2. Solve a small online quadratic program to stay close to intention while satisfying constraints. 3. Convert the safe control into RDW gains. And 4. Use a relaxation mechanism for rare infeasible cases. Let me unpack the key pieces, starting with the safety constraints. The core CBF idea is simple: define a time-varying safe set, a region where the user remains at a safe distance from every moving obstacle, and then enforce conditions that keep the system inside that set over time. Here the barrier is distance-based. If you get too close, the barrier becomes active. Next is the standard zeroing condition that guarantees forward invariance. To guarantee safety over time, we enforce the zeroing control barrier function condition. The barrier's derivative plus a scaled barrier term stays non-negative. Intuitively, as you approach the boundary of safety, the controller becomes more conservative and pushes you back towards safer motion. And the nice thing is this turns into a linear constraint on velocity. When we expand the time derivative, the condition becomes a linear inequality in the control, u. So each obstacle contributes a single linear constraint. Geometrically, those constraints carve out a convex feasible region. You can think of it as a cone or polytope of safe velocities. That means we can enforce safety directly and explicitly inside an optimizer, in real time. And that brings us to the online QP. The QP is simple: we choose a velocity, u, that stays as close as possible to the user's desired motion, u sub d, while satisfying all the CBF-based safety constraints. And because open spaces can get messy, think about situations where the user is nearly boxed in. We optionally introduce a slack variable to keep the problem feasible. Any violation is heavily penalized, so the solver only relaxes safety when it absolutely has to. But RDW can't directly control someone's legs, so next we map this solution into perceptually acceptable gains. The QP gives us a safe, optimal control, u-t. We treat this as an updated intention signal, and then translate it into standard RDW gains, translation gain, rotation gain, and curvature gain. Implementation details are crucial for comfort. First, we cap the gains so they stay within perceptual limits. Second, we apply low-pass filtering to smooth the signal and avoid abrupt changes. With that in place, let me move to the results, first simulations across multiple baselines, and then a real co-located user study. In simulation, we compare DyCoRe against 7 representative RDW methods using standard metrics, reset count, distance between resets, and time between resets. The headline is, DyCoRe yields the lowest reset counts and improves continuity under dynamic obstacles. Let me highlight each metric quickly. Here's reset count. DyCoRe is consistently lower, fewer interruptions, indicating more robust behavior when obstacles move. Distance between resets trends higher for DyCoRe, meaning users can walk farther without being forced into a reset. Time between resets is competitive. Overall DyCoRe is strong on stability, especially in reset reduction. In simulation, DyCoRe is especially strong at reducing resets and keeping behavior stable. Time between resets is competitive, but the bigger, most consistent win is fewer resets. Of course, simulations only tell part of the story, so we validated the method with real users in a large outdoor open space. We conducted a paired, within-subject user study with 30 participants in a large outdoor open space. Participants were paired and walked simultaneously in a shared tracked area under 4 conditions: DyCoRe, S2C, S2O, and TAPF. As you can see here, DyCoRe significantly reduces reset counts, and increases both the distance and the time between resets. Statistically, we observe significant overall differences across all 3 metrics, and DyCoRe outperforms each baseline in pairwise comparisons after correction. So the key takeaway is that the safety-constrained formulation translates into better real-world motion continuity, less interruption, longer continuous walking. Let me zoom in on the reset count first, the left panel here. Lower is better. DyCoRe has the lowest median and a much tighter spread, which means fewer interruptions and more stable walking. And the asterisks indicate the differences are statistically significant versus each baseline after multiple comparison correction. On the middle and right panels, we report distance and time between resets, so higher is better. DyCoRe achieves a substantially higher VDBR, meaning participants can walk farther before any reset. And it also delivers a longer TBR, so they can keep walking for longer stretches without interruption, again with significant improvements versus the baselines. So objective continuity improves, but we also care about how users feel. Here's the experimental setup and what participants saw: a large outdoor open space with 2 users moving in the shared area. On the right is the SSQ radar chart. Larger radii mean more severe symptoms, and the items A to P cover discomfort, fatigue, headache, nausea, and different types of dizziness. Overall, DyCoRe tends to produce lower SSQ scores across most items, especially headache, nausea, eye fatigue, and dizziness-related symptoms, suggesting improved comfort. To wrap up. First, we introduce OPS-RDW, framing RDW for large, open physical spaces with dynamic obstacles and co-located users. Second, we propose DyCoRe, which uses dynamic CBF safety constraints plus online QP optimization, then maps the solution to RDW gains to balance safety and natural walking. Finally, through simulation and a real user study, DyCoRe delivers better motion continuity, fewer resets and longer uninterrupted walking, and tends to reduce discomfort. DyCoRe is effective in our tested settings, but scalability may be limited in very dense crowds, and we currently rely on fixed, hand-tuned parameters without online adaptation. Also, broader validation is still needed under real-world noise and latency, and we assume a managed tracked space. Next, we plan to add adaptive tuning, model richer crowd interactions, and validate in more uncontrolled deployments. Thank you for your attention. I'm happy to take any questions.